Hi folks, Mr. Long here. This is a screencast on part C of related rates, the measurement problems. We could work with many different shapes, cylinders, cones, spheres. We're going to focus on spheres. They're a little bit easier on average, but there's some interesting parts to them. So to the problems. So let's go through this, and we're going to go through the same five-step process that we went through before, except this time I'm going to write it out as if you would write it out on a piece of paper, because you're not always going to have that worksheet with blank spots in it to fill in. So we've got a balloon that is a classic related rates problem. Think of a balloon that's being blown up with air at a constant rate. So clearly not a person blowing it up, like breathing in, breathing out. It's hooked up to, it's like a basketball getting blown up by an air compressor. And what we know is if we take this information up here, it says at a certain time the volume is 360 centimeters cubed. 20 seconds later, the volume is 450 centimeters cubed. So there's something that they're getting at there. I don't know, let's see, maybe I'd want to highlight that. At a certain time, the volume is 360, 20, and then later on the volume is that right there. So there's something there, 360, 20 seconds later. To me, that's looking like a rate, right? We know how much the volume is growing at per 20 seconds. And then it says, the question actually says, find the rate of increase of the surface area when the balloon has a volume of 1,500 centimeters cubed. So it's time to go through the problem. And so one of the things that we do is we draw a diagram to start. Always phase one is always to draw a diagram, right? Over there you can just see the word diagram. Variables, constants, any rates that you know you should list. So to me, what's really important here initially is oops, there. What we want to know is list down the constant. So we know that the issue is when it's 1,500 centimeters in volume. That's when we want to know the rate of increase of the surface area. Um, some other information that we want to know is we're supposed to list any known rates here. Well, it's not a known rate, but it's awfully easy to figure out because the volume grows from 300 and, oh, by the way, the other thing that's important here, I should have mentioned this, that is it's at a constant rate. Okay, it's at a constant rate. So that's why we know when it goes from 360, from 360 up to 450 centimeters cubed, in 20 seconds we can get the rate, right? We know what the rate is. And so we do that division. 450 minus 360 is 90. 20 goes into 90. It's the same as 2 going into 9. So that's 4.5 centimeters cubed every second is how much air is being blown into that balloon. So, so we know that. Now something else that really I didn't do last time, but we need to add this to these types of questions, the measurement questions. Any relevant formula really should be listed right off the bat. So if you look at this question, we talk about volume and they talk about surface area. So clearly those two formulas, whether you use them or not, I guess is not that important. But what it is important is that you actually write them down, right? So we should do our volume formula for a sphere. Volume equals 4/3 pi r cubed. And surface area, now this is part of part one, surface area, oh, equals, now surface area is the rate of change of volume, which is interesting. I was going to deal with that later, but we can just see if you can make the connections there. 4 pi r squared. Interesting. So take a look at how those two are related. So those are some formulas that are important, volume and surface area for a sphere. The second part always is to list any of the rates and to develop that chain rule. Now with this, what I'll do is I'm going to bring, whoops, bring that there. So in the question, we know this. So number 2 is when we go through all the rates and we develop the chain rule relationship. So if we look at it, dV by dt is given as 4.5 centimeters cubed per second. It wasn't given, but it was an easy calculation. Then our goal. So we always want to go with what are the given rates, what is the goal rate? What rate do we want to figure out? Well, we want to figure out the rate of change of surface area with respect to time. And that's given right in the question. That's our goal. So I call that dSA by dt, rate of change of surface area with respect to time. And so I always start by start with the goal rate that you want to get, dSA by dt, and start with what's given, dV by dt. So if we take a look at this, we want to get dSA on the top. Okay, so we're going to have to, the next rate that I'm going to develop here is going to have dSA on the top. Okay, so dSA on the top, and then what about the bottom? We're going to have, look at our formulas that we have. Can we get a rate of change with surface area? Yes, we can. And surface area is going to be related to radius. So it's going to be dSA by dr. Okay, so we know that. And then we ask ourselves, are we done? Is that enough? Do I only need two rates on the right side? Well, if I look at this, I don't have anything canceling out yet, right? So that's a bit of a problem. So I need to start canceling things out. So I need to have a rate because I need to keep dSA and dt, right? So I need to be able to, and I'll just maybe put a line through it here. I need to be able to get rid of dV, and I need to be able to get rid of that dr. So it's pretty obvious what I need over here then as that third rate. What will it be? It's going to have to be the opposite of that, the reciprocal rather, not opposite. It's going to have to be dr by dV. So now if I have dr by dV, I can actually, dr divides out with dr, dV here divides out with dV here. This is worthwhile pausing and taking a look at to see how this was developed. So again, I'll go through that. I'll go through it once more. Our goal is what we start with. That's what we want to, in the end, we want to figure out dSA by dt. Now what we're going to do with that is start with the known rate that we have, the actual numeric rate that we have, which is dV by dt. I know that I want to end up with dSA on the top, so I need to start my next rate with dSA. And then I have to look at my equations and see, well, what kind of a rate can I get from surface area? Well, surface area is on the left and r is on the right, so it's going to be the derivative of surface area with respect to radius. Once I do that, I take a look at, okay, well, this is the dSA by dt, and in our cases before, these two we've always been able to cancel those out, right? But it didn't cancel out this time, so we need a third rate. And the third rate is going to have to be the reciprocal of dV by dr in order for it to divide out. Okay, so that's really nice chain rule analysis here, and it really forces you to understand the chain rule, which I think is quite important. So let's move on to the next phases, which are 3 and 4. So in steps, well, we'll do step 3 here first. Step 3 is really to list the equations and their derivatives. And then we're going to see what we can do in terms of using them. So the equations that I know that I can use are the volume equation and the surface area equation. By the way, let's go through and actually differentiate now. Let's differentiate the volume equation. So all we're going to do is differentiate r cubed, and that's going to multiply by 4/3 pi, because 4/3 pi is just really a coefficient. So r cubed is 3r squared. So I've got a 3, and then I've got 4/3 pi. Whoops. 4/3. Oy. Let's get rid of that. We'll get rid of that and get rid of that. Yeah, why don't we get rid of that too? So after that messiness there, let's go ahead and write this down. So again, the coefficient was 4/3 pi, and then I need to differentiate r cubed. So that's just going to be 3r squared is the derivative of r cubed. So let's look at this. So that divides out there, that divides out there, and I'm left with 4 pi r squared. So 4 pi r squared is actually the surface area of a sphere, which is the rate of change of volume. Pretty interesting. And of course I wrote that down over here as well, just for you to see it. Okay, so we started with volume. We have surface area here, which is 4 pi r squared, and we have to do our rates of change. So the rate of change of volume is dV by dr. The rate of change of surface area is dSA by dr. 4 pi r squared, 2 comes to the front. It's 8 pi r is the rate of change for surface area. 4 pi r squared is the rate of change of volume. Now, what we have to be careful of, what rate do we actually want? Well, the rate that we want is dr by dV. I don't want dV by dr. I want dr by dV in my formula. So what I have to do is put 4 pi r squared over 1 and do the reciprocal of both sides, so I get dr by dV. And then I also need dSA by dr, and it's worth 8 pi r. Okay, so I know all my rates that I need. The two rates that I need are these two. So I need that, and I need this, and that's going to go right into my chain rule, which is the next step. So again, phase 3 is listing the governing formulas, as I like to call them. So in this case, it's volume and surface area, and then we get the rates of both of those. And we look what we might need to do to manipulate. Okay, last two phases, 4 and 5. Now, 4 is what we do is we write out the rule, the chain rule, and then we look at, we substitute in the new formulas that we have. And so the formulas for our rates, and we look at what's missing potentially. So we might need to figure something out. And the final step is just to substitute all the numbers into the chain rule and get your final answer. Okay, so as we do this, dV by dt, that was given, 4.5 centimeters cubed per second. And then we have this one here, dSA by dr, which we figured out was 8 pi r, centimeters squared per centimeter. Why are those the units? Because it's surface area, centimeters squared there, over radius, which is centimeters. And the final rate was dr by dV, and that's 1 over 4 pi r squared. Now, what are the units on that one? The units on that one are going to be something interesting. So it's dr by dV. So it's actually centimeters over centimeters cubed. So if we look at this, look at our units and see if we've done it right. Centimeters and centimeters. And then I've got centimeters cubed there, centimeters cubed there. So the centimeters cubed divide out. And I'm left with centimeters squared in seconds on the bottom. Rate of change of surface area with respect to time. Okay, so what other things can I divide out? Well, the pi there and the pi there divide out. And let's see, that 4 goes into that 8 twice, so I can get rid of that and get rid of that and put it 2 there. And what I've got is 4.5 times 2 times r divided by r squared. Okay, if you can see that, the blue is the r. So 4.5 times 2 is 9. And then I've got r times 1 divided by r squared. So that's going to be over r. So that's the rate of change with respect to time. That's what the rate of change that we want to get reduces to. So if you multiply those three things, those three rates, you'll just get 9 divided by r. Okay? Now, what's the issue? We don't know r. So how do we get r? Well, it was given in the question that the volume was 1500. The volume was 1500. You know, I'll maybe move up here so it's a little bit bigger. So the volume is 1500. So I know that 4 thirds pi r squared, r cubed rather, is 1500. Now, how do I isolate for r? 4 divided by 3, so that means I'm going to have to divide by 4 and multiply by 3, right? That's inverse of 4 over 3. That says multiply by pi, so we will divide by pi. And this says cube, and the inverse of that is going to be the cube root. So I take my calculator. If you have the black calculator, the TI-36 Pro, it's quite easy. You just type that in math text, and you're going to get R equals 7.1 centimeters. Okay, so then I can, my last step, so what that is again, what do? So you get a simplified version of the rate that you want, and then you notice in the formula, is there anything missing that I had to figure out? Yeah, I had to figure out R. And so we look back in the original question and see, is there information there that will allow me to figure out R? And there always is, right? There always is. And then we just did grade 9 inverse operations to solve that. Okay, so dSA over dt is 9 over R. Well, that's 9 divided by 7.1. Okay, and that's going to be centimeters squared per second, and that's the rate of change. And I haven't calculated that out. You would just calculate that out to one decimal place. That's as far as we've got in terms of significant digits. Okay, folks. So that's a long one, 16 minutes. But again, I'm trying to explain step by step, and hopefully that helped. And I would go back over this one. Make sure you write it all out, and you have a good set of notes for this problem, because you're going to have 4 other problems that are similar to this. We're just going to focus on spheres. Okay? Have yourself a good night. Good day.